Hello everyone, Aaron here and welcome back to Leetcode. Today we are doing the maximum ice cream bars problem. It is a sweltering summer day and a boy wants to buy some ice cream bars. At the store there are n ice cream bars. You are given an array costs of length n, where costs I is the price of the ith ice cream bar in coins. The boy initially has coins to spend, and he wants to buy as many ice cream bars as possible. Return the maximum number of ice cream bars that the boy can buy with coins. Note, the boy can buy the ice cream bars in any order. So for example here, 1, 3, 2, 4, 1, these are the costs of the ice creams. He has 7 coins, so he can buy 4 of the bars. 1, 3, 2, and 1. If he buys the 4, he's spent too much money on one ice cream, and so can't get many more ice creams. Here, the bars cost 10, 6, 8, 7, 7, 8, for a total of 5 coin. With 5 coins, he can buy 0 ice creams. He can't afford any of them. And here, all of them... hang on, what's going on here? He can buy 6 ice creams. 1, 2, 3, 4. Oh, he can buy all of them because, as it says here, the sum is 18, which is less than 20. So, well, okay. Before I go completely silent, trying to work out what I'm trying to say here. Basically, the immediate thing that leaps to mind that I want to do is sort them, then take as many as I can while the sum is less than the number of coins. The hesitation I'm having is that I'm not sure that's actually the maximum. No, it must be the maximum. No, I've got myself slightly confused here. So, if we have our 1, 3, 2, 4, 1, if I sort these 1, 1, 2, 3, 4, the running sum is 1, 2, 4, 7, 11. So I can take the first 4. And that's my cost of 4. In fact, this would be very amenable to an APL solution, which would be something like sort them, then do the running sum, and then you'd want to find all of the ones that are less than or equal to the number of coins. So that's less or equal, that's less or equal, that's less or equal, that's less or equal, that's not. And then you want to sum them up, and that will give you 4. So that's quite nice. The question is this maximal? Now, I'm not going to do a full proof because I don't know if I could do a full proof. There's my discrete maths proof theory stuff is a little rusty. But I think there's an argument here that let's assume this wasn't maximal. Then we should be able to include this in some way, which would mean taking all of these has somehow left us with enough coins to buy this as well. But that's impossible because the next thing we would buy would be the minimum amount we could increase the number of coins by, increase the cost in coins by. I'm not making a huge amount of sense here. I'm aware of that. So let's say we've bought some X using our above strategy, but it is less than some optimal solution that was not using our strategy. So the composition of ice creams here must be different to those here. But we know this contains all the lowest cost ice creams. So this must include an ice cream that costs more. In fact, it must include 2 ice creams that cost, at least 2 ice creams that cost more. No, at least 1 ice cream that costs more than any ice cream in this set. But we could not afford that because we have been as judicious as possible with our coin usage. Okay, so I don't know if I've been at all clear, but I have convinced myself that this algorithm will produce the maximum number of ice creams that the child can buy. So, costs.sort. That's the first thing we want to do. We want to get these in order. That's from here to here. Then, I'm not going to do this running sum and less than or equal to business, but the count is going to start at 0 and the total is going to start at 0 for C in costs. Tot plus equals C. If total is greater than the number of coins available, return count. Otherwise, what we want to do is we want to increment count. And if we get to the end, return count. So we want to take the first one. If that has exceeded the number of coins, then we have to give up and return 0. Otherwise, we say we're going to take that ice cream. Then we're going to go again. Sorry, that's right here. These now add to 2. Does that exceed the number of coins? Nope. So we're going to say we've now taken 2 of them. We're now going to look at this guy. The total cost would be 4. Does that exceed the number of coins? No. So we're going to add that. We're going to take 1 more. This one here. We're going to add that on. Total is 7. Does that exceed the number of coins? No, it doesn't. It's equal to the number of coins, but it doesn't exceed it. So we're going to add 1 to the count and carry on. This one here, we're going to add that to the total. Does that exceed the number of coins? Yes, it does. So we have to stop and return the 4 ice creams that we've already purchased. If we make it all the way to the end, that means we could buy all of them. So we can just return the count. Let's submit that. Perfect. I don't think this should be a medium problem. I think this should be an easy problem. Yeah. Although, holy moly, I'm slow. What could I do quicker? There is literally nothing here that's expensive. The only way I can make that faster is somehow to knock out the sort, but I really don't know how you could do it without the sort. I don't know. Anyway, that I think isn't too bad a solution. It's very tidy. It's very easy to understand. You don't need all this crap. I'm happy. I'm happy with that. Do let me know how you did it. How did you get down into this big bunch of fast movers? I don't know. They must have done something with a lot of memory because we've done very well on the memory scale. I don't know. Anyway, that's it from me this week. Do remember to like, comment, subscribe, all of that good stuff, and I will see you next time. Bye.